Hi everyone, in this video we'll solve example 3.5 from the book Applied Thermodynamics, McConkey and Eastop. Here is the statement of the example 5 from chapter 3. Air at 1.02 bar, 22 centigrade, initially occupying a cylinder volume of 0.015 meter cube, is compressed reversibly and adiabatically by a piston to a pressure of 6.8 bar. Calculate the final temperatures, final volume and the work done on the mass of air in the cylinder. Let me first write the data that is given and what that is asked in the statement. Pressure P1, that is 1.02 bar. Temperature T1 before the compressions is 22 centigrade. To convert it into Kelvin, simply add 273 with it and it is 295 Kelvin. Initial volume before compression 0.015 meter cube, and after compression the final pressures obtained is P2 and it is 6.8 bar. What we need to calculate is to the final temperature T2, final volume V2 and the work done on the mass of air in the cylinder. How much work is supplied to the compressor in order to compress this from pressure P1 to pressure P2. Let me draw the PV diagram for this statement. Initially the volume of the gas was very high, that is, let's say V1, and then it is compressed and reached to the final state gamma is equal to constant. As it says in the statement, compression is taken place adiabatically. This is our initial state, this is our final state. The volume here is V1, the volume here is V2, the pressures here is higher pressure, that is P2, is 6.8 bar. Here the pressure is P1. The area under this curve represents the work that is required in order to compress the gas from initial state to the final state. Now let's come toward its solution. Since there is adiabatic compressions from state point 1 to 2, then the relationship between temperatures and pressures of the final and initial state is given as the working fluid is air, then for air the gamma value is 1.4. So just put this in this formula and you will get the final value of T2. What is T1? That is 295. T2, after solving this on calculator, you will get its value, that is 1.7195. Multiply this with 295 Kelvin initial temperatures, you will get the final state temperatures and it is 507.3 Kelvin. There is adiabatic compression. So there is adiabatic compression, then the relationship between the pressure and volumes of the initials and the final state is P1 divided by P2 is equal to V2 divided by V1 into gamma. Take gamma root both sides, so this will be cancelled out with this and you will get V2 divided by V1 equal to P1 divided by P2 into 1 over gamma. Now just simply put the values. And arrange these equations for V2. Solve this on calculator, you will get the final volume, that is V2 and it is 0.0038 meter cube. Now from first law of thermodynamics, heat plus work done is equal to change in internal energy. This is adiabatic compression. Then the heat in or out to the system is 0. Then we can say that the work input is equal to change in internal energy and it is equal to CV into change in temperature. What is CV value? CV value for air is constant and it is equal to 0.718. Just simply put the values of CV and T2 and T1 value. T2 is 507.3 minus T1 value is given, that is 295 Kelvin. To solve this on calculators, you will get the work input to the compressor in order to compress the air from initial state to the final state from pressure P1 to P2. We will get the values of work input, that is 152.4 kilojoule per kg. Next we need to find the mass, how much mass of air is present in the cylinder. That is equal to P1 V1 is equal to mR T1. Rearrange this equation for M. What is P1 value? That is 1.02 bar. Multiply 10 to the power 5. What is V1? That is 0.015. And the R value of the gas is constant, is 287, and multiply with the initial temperature, that is 295. After solving this, you will get the mass of the air that is present in the compressor cylinder, and it is 0.0181 kg. Now the total work input required in order to compress this air, that is equal to M multiplied by specific work done. The value of M is mass of air is 0.0181 and work done per kg is 152.4. After solving this, you will get the total work input required in order to compress this air, that is 2.76 kilojoule. And this is our final answer. I hope you understand. If you still have any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed yet.